Thank you very much, Itzik. I'm truly honored to invite our first speaker, Professor Artur Ekert, both from the Center for Quantum Technologies in Singapore and from the University of Oxford, one of the founders of quantum communication and cryptography, winner of many prizes. I don't think that's what people are waiting for, so I'll just let you have it, and let's see if we can find the...
Right, okay.
So I'll give you a 5-minute mark.
Okay, well,
if you need it.
Well, I may. We'll see how it goes. Well, thank you very much. Thanks to the organizers, to Itzik and his colleagues for inviting me to come over. And to hyper-efficient Ilana, I think, every single institution has the person that if you have any questions, the answer is, you go and ask this person and the answer comes quite, I think she violates causality. Sometimes I get the answer even before I ask the question. So thank you very much, Ilana. And so it's a great pleasure actually to come and give this opening remark. Itzik mentioned that I may talk about quantum crypto, but actually I'll talk about the other side. I'll talk about quantum computing and perhaps what kind of challenge it poses to conventional crypto systems. But because you gave such a wonderful introduction about quantum physics and non-locality and all those issues, so I think that, that's very helpful. And as you pointed out, that it's very difficult to preach to a very mixed congregation, like in this particular case. How many of you are really physicists? You will identify yourself as physicists? Well, not so many. Wow. So how many of you would identify yourself as computer scientists? Okay. So here we are. So now I have to just explain quantum to computer scientists. Well, it's not an easy task. And I think I like your approach, that you do it not so much talking about physics, but thinking perhaps about quantum as a new way of taking more mathematical approach and thinking about it as a new way of calculating probabilities. So let me take this approach and say a few words about the quantum technology. So maybe I should be more systematic and start with this slide. So the first message I want to convey in this very brief talk is that whatever you think, you have no escape from quantum technology because it's going to happen. And the reason for that is that in our quest to domesticate nature, to control nature, we have to hit quantum phenomena sooner or later. And it may happen sooner than later. In fact, we are already controlling a huge part of the quantum world. And of course, quantum physics is universal. It doesn't necessarily, there's this misconception that you have to go into a microscale to see quantum. It is indeed the case that the quantum phenomena are very conspicuous if you go to a micro, but it is, to the best of our knowledge, the universal description of nature, applying both to macro and micro and macro scale. So if you take this simplistic view that, for example, in computer technology, you want to build smaller and smaller devices, and you may argue, well, I want to make them really small because I want them to communicate really fast. And I know that there's an upper bound on communication. The components cannot communicate faster than with the speed of light, right? So therefore, I just cram as many as I can into a given volume, so that's good. Of course, it is good, but what is good about it is not because you're just cramming more and more components into a given volume of space, but what is interesting is that at some point, when you just go from this level of silicon wafers to nanotechnology, and then you go into the world of molecules and atoms, what is really interesting and fascinating about it is actually that the physics somehow is different. You discover your classical intuition, your intuition that you build up from everyday experience doesn't quite work. And physicists had to work very hard to build some kind of a model for this reality. So once we cross to that... let me just see. You see, I have a problem with classical technology. Huh? Okay. So the thing is then, you know, once you just cross this imaginary non-existing border between classical and quantum, and as I said, quantum is universal, so this sort of fictitious border doesn't really exist. But you know, once those quantum phenomena become conspicuous enough, you may just wonder, what are you going to discover this? What are we after? And my predecessor nicely mentioned that basically there are two things that physicists are excited about and computer scientists think about as two new resources. That is pretty much quantum interference and quantum entanglement. So the entanglement can be understood as a quantum interference where you have many components, many particles. But perhaps to computer scientists, as most of you are computer scientists, the quantum interference is the most interesting part because what it really means is that it shows you that the classical conventional probability theory doesn't quite work. So you know that if when you are taught probability theory, that depending how you approach it, but usually you go through Kolmogorov axioms, right? So then probability is a number that is a non-negative number, and then there's this one essential axiom which says that the probability of mutually exclusive events add up, right? So I don't have a slide, but let me just draw something here. So you know that if I have event, then something can happen in two different ways. So there's one way and another way, and you attribute probability P1 to one event, and there's a mutually exclusive event, so P2. So then the probability that, say, a particle that has a chance to go from this place to this place, and it doesn't have to be a particle. Any system, think about it as a configuration space. You start from initial condition. It could be a computer, right? A Turing machine or something. So this point is just a specification of the state of this device. And suppose that this machine has a chance to evolve in taking one computational path with probability P1 and taking another computational path with probability P2. So then, if you use Kolmogorov axiom and you say, okay, those two computational paths are mutually exclusive, then you say, okay, I will end up in this particular output here with probability P equal P1 to P2. And that's what you learn from a classical probability theory. Now, quantum physics, if you want to forget about physics, quantum theory, right, for computer scientists, is a different way of computing probabilities. Basically, instead of talking about probabilities, you talk about probability amplitudes. You talk about complex numbers, and you have to take mod square of this complex number to get probability. Except that in this particular case, when you have two different alternatives, two mutually perhaps exclusive events, and I said two mutually perhaps exclusive events, I'll come back to this perhaps, then you add probability amplitudes and take mod square. So in other words, what physicists guessed, and what we do today is, if you want to make proper statistical predictions, then you have to just simply acknowledge that Kolmogorov axiom, additivity axiom, doesn't work. What does it mean? It means that nature doesn't know about it. Nobody told nature about Kolmogorov axioms. It's, it's a mathematical theory, right? So mathematically speaking, it's just for consistency and everything, it works, but you don't question axioms. But it's a valid question to what extent your mathematical model corresponds to reality. And the answer is, well, it doesn't. The additivity of probabilities is, in many beautiful experiments, like in double-slit experiments, it's just violated. So what you do instead, you take a complex number, alpha 1, called amplitude, and alpha 2, and you say, well, the system then goes taking one of those two computational paths, or perhaps both of them, but you attribute amplitude alpha, which is alpha 1 plus alpha 2. So you modify this Kolmogorov additivity axiom by adding amplitudes, not probabilities. And you say, okay, what the difference does it make? Well, it does, because then those are complex numbers, and you remember the probability is just mod square of it. So the probability P is mod of alpha 1 plus alpha 2 mod square. And if you just do this, that's a very simple, even, I mean, in computer science, you learn about complex numbers and so on and so forth. I'm just, I don't want to insult computer scientists, so my apologies. And,
I can do third time.
I did already? Oh, my apologies, this is the worst thing. I just, I know. Sorry, it's just, the worst thing you can happen. You are invited and you insulted. But, so what you do here is that, by the way, I'm trained more as a mathematician, so it's just... So when you do this calculation, so it's going to be like alpha 1 mod square plus alpha 2 mod square plus the cross term. So it'll be like alpha 1, alpha 2 complex conjugate plus alpha 1 complex conjugate alpha 2. So you see, this term here, so you see we have two terms here. Look at this one. So this one corresponds to P1 and this one to P2. So the first part of this formula is the classical additivity. I add probability, alpha 1 mod square is P1 and alpha 2 mod square is P2. So indeed the first part is just adding probability, but there's this one called interference term. And this one could be either positive or negative. And if it is a negative, then the total probability is less what it would be classically. And if this term here is positive, the probability would be more than it would be classically. And we are going to take a big advantage of this, because what is quantum computing in a, if you really want to simplify the whole thing, is imagine a device, a machine that has a number of configurations. You start in some initial configuration, that is your input. And classical deterministic computer would just go from one configuration to another, to yet another, and will end up in some final configuration, which is called the output. Now, you can also do computation in a randomized way. Computer scientists are very familiar with randomized and power of randomized computation, where you can use probability, in which case your computing device may take different trajectories with different probabilities. And then you add up probabilities, which is fine. However, if you can control quantum phenomena, if you can do this in such a way that this is a quantum process, then you have here an extra degree, an extra handle to play. Simply because you can use quantum interference. Not only you do computation in a randomized way, but if you're clever enough and if you pick up the phases of those complex amplitudes properly, you can amplify probabilities of correct outputs by constructive interference, and you can decrease the probability of wrong outputs by destructive interference. So simply, a quantum computer would really just follow all those different computational paths, and the art of quantum computing is to make sure that you have constructive interference on the output that is just the right one. How to do is another story, of course, but conceptually that's what quantum computation is about. So you may think about the progression. Classical deterministic computation, you just have one path. Then the second one would be randomized computation using probability theory, in which case you may have different computational paths taken with different probabilities, and you add probabilities, you just apply Kolmogorov axiom. And in computer scientists know very well that there's the whole area of randomized computation. It's still an open problem whether inherently randomized algorithms are more powerful than the classical deterministic algorithm, but we know a number of them that perform better, but there's the whole de-randomization program in people working in computational complexity. Now, the quantum one is just adding an extra layer to randomize. We say Forget about adding probabilities. That's not how the world really works if you go into details. We have to add probability amplitudes. And by doing so, we have this additional extra handle to play. We try to get constructive and destructive interference on certain outputs. And that's how we think about quantum computation. So this kind of thing, what is it good for in general? What are those quantum phenomena good for? Not only for the process of computation, but in general. Well, the fact that you can use quantum interference and quantum entanglement you can actually use to your advantage. So we know, for example, when you talk about privacy, usually we talk about quantum communication. We can talk about certified randomness. We can talk about device-independent security. There's just the whole beautiful area how quantum physics can provide you, or quantum theory can provide you with secure communication, but also how quantum computing can perhaps affect secure encryption. Probably what is more practical today is the area where you talk about sensors. So, using entanglement, you can design high precision atomic clocks, for example, or frequency standards, or various sensors and devices. You can show, in fact, that if you manage to, the modern quantum atomic clocks are based on trap ions, where you just probe a certain transitions in those trap ions, and then if you can entangle them, if you entangle n of them, you are hoping for something like the square root of n improvement in precision. So there are all kind of sensors that you can actually play with. And then, of course, at the end is just a quantum computing that I was talking about. So what people call the second quantum revolution is this ability not to use the fact that energies are discrete. That's actually the least interesting part of that. It's just ability to play with quantum interference and quantum entanglement, which actually experimental physicists are now coming to, are increasingly more able to do so. And this actually gives us a fantastic insight into new possibilities to play with. Let's see. So, the last two slides are really about the impact of quantum computing on security as we know today. So you probably know that using this quantum interference that I described, you can design an algorithm. One of them, or a different variation of Peter Shor's algorithm, affect the public key crypto systems, like based on discrete log or elliptic curves or factoring. So RSA elliptic curves. That kind of mathematical problems upon which we build security are not will not be considered secure anymore. And it's actually an interesting problem what kind of mathematical problems will lend themselves into quantum immune public key crypto systems in the future. As you know, this is actually a very interesting problem. People are betting on maybe lattice-based crypto systems or some error-correcting code-based. So it's not entirely clear. And the reason why it's a difficult problem, it's not only just to assert that this is a difficult problem and maybe we can have a next generation of public key crypto systems based on it. The problem is also to understand the power of quantum computing. Okay, 5 minutes. Yeah. So this is my last slide. So this is actually a slide that I got from a former student of Mike Mosca, who in this context, in the context of this story, that you have this potentially very non-existing in practical terms, but potentially very powerful device like a quantum computer that can affect the crypto systems that we use today. And the question is, should we worry about it? So Mike actually summarized it in a very nice way, say, well, there are 3 parameters you have to look at, and then consider that parameter X, how long do you think you need your cryptographic keys or your data to be secure? What kind of time scale you are talking about? And of course, it differs. It's from financial transactions, it's a different time scale. From medical record, it's a different time scales. For national security is a different time scale. So you have to make a decision, what is your X? Then you have to look carefully and pick up your second parameter, that is Y. So it depends, what is, how much do you think it will take to retool the existing infrastructure to sort of a large-scale quantum-safe solution? So what would be the time needed to implement quantum immune infrastructure? So call it Y. So it depends. It's not only about technology; it's also about implementation. How long does it take to have a certain system of standards in place, and so on and so forth. So call it Y. And then the second and then the third parameter you have to look is parameter Z, which says, how long do you think will take experimentalists to build a quantum computer that will be powerful enough to factor large integers? And that's parameter Z. Okay, so now if X plus Y is greater than Z, then you have to worry. So that's actually as simple as that. Now, of course, depending on whom you are talking to, people will give you different values for X, Y, and particular Z, which is a very difficult parameter to estimate. How long will it take to build a quantum computer? My answer is I really don't know. I think it's not going to happen within the next 5 or 10 years, but probably will happen before 50 years' time or so. We're talking about fully coherent quantum computer that will be a real challenger to RSA, not just few quantum noisy gates that can do something interesting, possibly something even that you cannot do in a classical way, but nonetheless not powerful enough to threaten the existing crypto systems. So I will leave you with this, what I call the Mike Mosca equation, in honor of Michele Mosca, that if your X plus Y is really truly greater than Z, then you have to worry. Otherwise, you don't have to just be disturbed in your sleep. Thank you very much.
Thank you. We have time for 1 or 2 quick questions, please.
Well, a lot, in fact, because if you think like this quantum thing, if you take, for example, Bitcoin, so that you would have at least 2 factors. For example, you need elliptic curves are used for digital signatures, right? So they're not going to be secure if you have quantum computer. The other thing for mining purposes, when you can use a Grover search algorithm to perhaps distort or manipulate you can probably manipulate the mining process and undermine the whole integrity of Bitcoin.
How close do you think they are to using quantum technology to have financial solutions based on quantum?
Not close. So I would say that for another 5-10 years, probably.
Another question?
Well, sorry, just to add to your thing. If you think, if my estimate is perhaps conservative, if it is shorter than that, there are fixes available. So for example, you don't have to base digital signatures on elliptic curves. You can actually go for lattice base, which at the moment we don't know how to use quantum technology to crack a lattice base, even though, it's an unsolved problem. Maybe it will be able to do. But there are fixes available.
Maybe I'll leave a comment and I'll ask a question. One comment is that we're talking here about code breaking and security, which is interesting to many people here, but there are other things to worry about when it comes to the abilities of quantum computing, abilities that will come much sooner probably than this specific application. My question to you is, what do you think is the technological bottleneck for quantum communication systems to become widely spread and used?
For quantum communication, I think that that will come to probably, in my personal view, actually, if you are looking for the next generation of quantum crypto, which going in the direction of device independence, so that would be the detector efficiency and the quality of entanglement that you can get. I think that would be a crucial limiting factors for that.
again.